Today's topic is mass spectrometry. It is an analytical technique which measures mass to charge ratio of the charged particles. By mass spectrometry, we can find out the masses of the particle, the elemental composition of the sample or the molecule. So it is very important for elucidating the structure of different molecules. Now let us come to the principle of mass spectrometry. As you can see the equation in which high energy electrons they will be colliding with the molecule, and then it will ionize into what is known as the molecular ion, the neutral pieces and the smaller fragments which are known as the daughter ions. So these are the molecular ions which further undergo fragmentation to give you the daughter ions. Now let us see how this works. Let us take an example of ethanol. So ethanol, when bombarded with high energy electron, first you will get what is known as the ethanol molecular ion, which further fragments into the daughter ions. So this is the m by E value of different fragments. So this will be shown in the mass spectrum of ethanol. This is the graph of relative intensity against m by Z or m by E value. So the first peak which we get, this one, is the molecular ion peak, which is of molecular ion or ethanol, which is having m by E value 46. Second is when one hydrogen moves, so second peak will be at 45. Then next one is the when CH3 group is eliminated, you will get a peak at 31. So it is showing maximum intensity. This will be chosen as the base peak. And after that, next will be when OH group departs, you will get a peak at 29. So this is how the mass spectrum of ethanol looks like. This is the instrumentation, which is consisting of the inlet system, then is the molecular leak, the ionization chamber, mass analyzer, and then the detector and the recorder. Now the sample which is injected initially, it is in the liquid state, but once it enters the molecular leak, here heater is there, it will vaporize the sample, so it will produce a steady state of vapor. And then in the ionization chamber, there will be beam of high energy electron, which we will get from the electron gun, and that will bombard with the vapors. So when high energy electron is bombarded with the vapors, it will produce the molecular ions, which will further bombard and give you daughter ions also and the neutral fragments. Now there are series of charge plates, so particles will be accelerated in the magnetic field, and then it will be subjected to what is known as the magnet. Now depending on the mass, heavier and lighter fractions, they will be separated, which will be converted into electrical signals by detector, and finally it is recorded by a recorder. So this is how the mass analyzer is used. So first stage will be the ionization, where the atom is ionized by knocking one or more electron off to give a positive ion, and then is the acceleration. This accelerating slit will allow the ions under study to accelerate so that they have same kinetic energy. Then they will be deflected by this strong magnetic field, and based on their mass, heavier fraction will get assembled at one place and lighter at other place, and then is the recorder. Now the detection is carried out by using various types of detector. Similarly, in ionization also various methods are there. Different ionization methods they are used. That can be the classical method or the modern techniques. Classical method includes the electron impact, fast atomic bombardments, which are not much in use nowadays, and the modern technique includes the atomic pressure chemical ionization, the electron spray, and MALDI, that is matrix assisted laser desorption process. So next we will be discussing these ionization methods. So this is the instrumentation, that is the inlet system, the molecular leak, the ionization chamber, mass analyzer, detector and recorder, as I've already discussed. This is how a mass spectrometer works. That is the sample. It's injected, ion source will make ions, mass analyzer will separate the ions, and then the mass spectrum will present the information. Working, as I discussed, there are four stages, sorry. First is the ionization, second is acceleration, third is the deflection, and fourth one being the detection. This is how the mass spectrum looks like. This is the mass spectrum of n-decane, for example. So graph is of relative intensity against m by z value. So first will be the molecular ion peak of the n-decane, and then fragments, that is CH3. In first fragment C2H5 will go, and then CH2 you have to reduce, that is 14 you are going to decrease. So the fragment which is formed easily, that will show maximum relative intensity, and that will be the base peak. Let us talk about the electron impact ionization. This is electron impact ionization source. It is one of the oldest method and was developed by Blickney in 1929. You can see here the electrons, they are emitted from the cathode filament, and they are drawn off the this is ionization chamber. They are drawn off the ionization chamber to the anode, and electric field will be maintained between the plates to accelerate the electrons. So subsequently, the collision of electron with, this is a sample of the molecules in passing the gas stream, it will produce ionization and the fragmentation. The field produced by plate B and a slight positive potential of the repeller R, it will remove the ions formed from the path of the electron beam, and they will be accelerated due to the potential difference between plates B and C, and then it will be fed to the mass analyzer. Next one is the chemical impact ionization, in which generally reagent gas is taken, and reagent gas, generally ammonia or methane is taken, that will be ionized, and this long reaction time will result in the ion molecule reaction between them, and that will result in the formation of ions, which on further bombardment will give you the fragmentation, and that will then go to the mass analyzer. This is an example of fast atomic bombardment. This was the first technique in which non-volatile compounds were used, and you can see here the atom beam is used for the bombardment. The analyte will be dissolved in the liquid matrix, and a small part of it will be placed on a metal sheet. You can see here, this is the metal sheet in which you are placing the sample matrix, and the ionization is achieved by high energy beam of xenon atom. So atom will be bombarded. So target is bombarded with fast atomic beam that will desorb the ion, and fragmentation will occur. You can see here the ion beams with these fragmented particles, and then it will go to the mass analyzer. This is electron spray ionization technique, in which an electron gun is used, and a sample will be put in this electron gun, and then the droplets of the sample, they will come out. This technique is used by creating high voltage on the flow of liquid at atmospheric pressure. So initially the droplets, they are of larger size, but when they move towards the electrode, they start shrinking in size, and because solvent is evaporating, and the droplet shrinks until it reaches the point where finally this droplet, it will break into smaller droplets, and finally all the solvent is evaporated, and then charge is passed onto the analyte. That will result in the fragmentation, and finally it will go to the mass analyzer. Next one is atmospheric pressure chemical ionization. This method is similar to electron spray ionization only, but instead of putting voltage on the spray, it is put on the needle. The sample is injected into the discharge by a spray created by the flow of liquid in presence of heated gas that will vaporize the sample, and the ions will be produced here in this case by proton transfer from hydronium ion or water cluster from the sample, and then that will move to the analyzer. This is matrix assisted laser desorption ionization technique, which is also known as MALDI. It can be used in two modes, which is either the linear mode or the reflector mode. In this technique, the sample will be bombarded with a laser beam, that is generally the nitrogen UV laser beam, and the sample actually initially it is mixed with the matrix, and that will absorb the radiation and it will transfer the protons to the sample, producing a singularly charged ions. And in order to accelerate the resulting ions in the flight tube in the mass spectrometer, they will be subjected to high electric field. So finally it will go to the mass analyzer. This is how the mass analyzer work. Different types of mass analyzer, they are in use. They analyze according to mass by charge ratio. So this is the magnetic sector mass analyzer. It is based on the principle that the charged particles, they are deflected by the magnetic field, and when the moving charge enter the magnetic field, they will be deflected in a circular motion. Because ions in the magnetic field, they are experiencing two types of forces. First is the force due to the magnetic field, and second is the centripetal force. So M by E will be given by its square, R square upon 2V, where H is the magnetic field, R is the radius of curvature, and V is the applied field potential. These are double focusing analyzer, the quadrupole mass analyzer. We call it quadrupole because it is having 4 poles. Opposite poles, they are similar in charge. This 2 will be plus, this is minus. So two pairs of charged quadrupole rods are there, which run parallel to the flight path. The opposite rod will have same polarity, and it filters the ions according to M by E value by just changing the voltage in the rod, and only the ions having selected mass to the charge ratio, that will have the correct oscillatory path, and then it will reach the detector. Next is time of flight mass analyzer, which the ions are accelerated in this case by flight tube to the detector, and time of flight will be measured. Obviously lighter ions, they will travel faster and they will reach the detector earlier. The diagram of time of flight mass analyzer showing the heavier and the lighter fractions. So lighter fraction, it is reaching the detector faster as compared to the heavier fraction. Next one is the ion mass analyzer, which consists of the ring electrodes and the cap electrode, which is hyperbolic in shape. Besides accelerator, next is the detector. Various type of detectors, they are in use, like the Faraday cup detector, the electron multiplier detector, then photomultiplier detector, and microchannel detector. In Faraday cup detector, you can see the diagram. The ion beams, they strike the cup shaped dynode surface. It will emit electrons that will induce a current. This induced current will be further amplified by the amplifier and recorder. This is the photomultiplier detector. In this type of detector, this dynode, it is made up of copper beryllium. So when a single ion beam is coming inside the tube, photomultiplier tube, it is passing through number of dynodes at increasing potential. As a result, finally we will get a beam of electrons from a single beam. This is an example of photomultiplier detector, in which photoemissive device, where absorption of photon that will result in the emission, of electrons, which will be further amplified into a photomultiplier tube. Again, photomultiplier tube, if a single beam is coming, it will be passing through number of series of diodes, and then it will undergo multiplication, and finally you will get beam of current, electrons. These detector can best detect the presence of metastable lines. There are certain rules for the fragmentation. Firstly, the height of the peak, that is molecular ion peak, that will decrease with increase in the branching. It decreases with increase in the molecular weight also, and the cleavage will be following this pattern, that is the carbocation stability will be of this order. Next rule is of Mac-Lafferty rearrangement. In this type of rearrangement, it takes place generally in the carbonyl compounds, which are having gamma hydrogen. So if this is a functional group, this will be alpha, this is beta, and this hydrogen is the gamma hydrogen. So it involves cleavage of beta bond followed by gamma hydrogen abstraction. So it is generally associated with the elimination of small molecules, and you will be getting formation of 6-member transition state, because this will shift here, this is shifting here, so this will become double bond here. So this bond is about to go, this bond is about to form. So transition state, it shows just the bonds which are about to form and the bonds which are about to go. This one is the retrodiol-Elder reaction, which takes place in the cyclic olefins, and that results in a multi-centered fragmentation. That is, this bond will break, it will shift here. Again, this bond will break, this will shift here. So two unsaturated fragments will be formed. This reaction proceeds by ionization, followed by the rearrangement of the double bonds. Rule which states that the molecule which is having odd nominal masses, they will give you odd number of nitrogen, and that with the even nominal mass, that will give you even number of nitrogens. We consider 0 as even only in this case. So you can see here, odd nominal mass is giving you odd number of nitrogen, even nominal mass is giving you even number of nitrogen. Besides that, there are many other rules, like double bond, it favors the allylic position. Alkyl substituent aromatic compounds, they show cleavage at beta position of the ring, and unsaturated rings, as I already told you, retrodiol reaction is seen. Whereas if saturated ring is there, then that loses alkyl side chain at alpha position. Then CC bonds, which are next to the heteroatom, they are cleaved, thus leaving the charge on the heteroatoms, and so on. These are the applications, like it is used in the identification of unknown compounds. You can determine the isotopic composition of a compound. You can find out the structure of the compound by observing its fragmentation, which are further confirmed by NMR and so on. You can quantify the amount of compound in a sample. You can determine the physical, chemical or biological properties. You can analyze the pesticides in food, soil by mass spectrometer. It is used in pharmaceutical analysis. So in this way, it is a very important analytical tool.